So this next related rate, we have a circle this time. We have the area of a circle increases at a rate of 3 meters squared per second. So this time we know what the area is doing. How fast is the radius changing when the radius is 4 meters? So our related rates, we know the rate that the area is changing, and we want to figure out how fast the radius is changing for that area to happen. So we need to think about a circle. This one is not as memorable as a square, I wouldn't say, but hopefully you know that the area of a circle equals pi r squared. So we have our function that relates our two things. Our area and our radius are related by a equals pi r squared. After we write that, we write out our variables. So we have the variable a. That's going to have a derivative of dA dt, how fast the area is changing with respect to time. And then we have r, and we're going to have dr dt, how fast the radius is changing with respect to time. So with this one, pi is not a variable. Pi is 3.14. It's just constant that keeps going, so it doesn't get any letters. So we have a and r, the area and the radius, and then there are two derivatives with respect to time. And we can see what we can fill out based on this information above. So the area of a circle increases at a rate of 3 meters squared per second. So the area increases. Is that going to be a or dA dt? Well, if it's saying increases, it's not a variable, it's a rate of change. So dA dt is going to be 3 meters squared per second. And should that be positive or a negative derivative? Well, if the area is increasing, that should be positive, 3 meters squared per second. How fast is the radius changing when r is 4 meters? So we're trying to figure out how fast is the radius changing because the area is changing. The radius is currently 4 meters. So I can put my units on this. dr dt, what we're trying to solve for, the radius is in meters, so dr is going to be meters, and then time for this one is seconds as well. I'm missing a variable. I didn't need the variable the last couple times, so I might not plug in to find it, but we could if we wanted to. If you're missing a variable, you plug into the original. What's the area? I guess we'll do it another time. We're missing a variable. If you ever need it, which we might not, because we didn't even use it the last couple times, you plug into the original. So we would plug into a equals pi r squared. So my r is 4 squared. So the area right now is pi times 4 squared. So pi times 16, or 16 pi meters squared for the area. If we need it, we might not even use it though. We're trying to find dr dt. So after we find our function and we write down our variables and our derivatives we're going to get of them, now we can actually take the derivative of the function with respect to time. So everything's going to get a d something dt. Okay, so the derivative of 1a is 1 dA dt. You can choose to write that 1 or not, because 1 dA dt is just dA dt. Next derivative, I need to keep this pi because it's a constant. It's like the derivative of 5x squared. You'd keep the 5, bring down the 2, you'd say it's 10x. Same thing with this. I'm going to keep the pi, bring down the 2. So I'm going to get 2 pi r, and then I just took the derivative of r with respect to time. So my derivative is 2 pi r dr dt. So now I can plug in and solve for dr dt. So I have dA dt is 3. That stands for 3 meters squared per second. And then I have 2 pi times my r, my current radius is 4, times dr dt, what I'm trying to solve for. How is the radius changing? So the last one was a little bit nicer because it was already solved for what we were looking for. This one I have to get dr dt by itself, which is not as bad as the implicit. I'm just going to multiply so that I can get it by itself. So first of all, I have 2 pi times 4, which is going to be 8 pi times dr dt. And now I need to get dr dt by itself, so I would just divide both sides by 8 pi. So the radius, dr dt, is going to be changing by 3 over 8 pi, and my units on that one are meters for r per second per time. So to interpret this as the area increases by 3 meters squared per second, you always say what's happening with the rate you're given first. So as the area increases by 3 meters squared per second, the radius does what? Does it increase or decrease in order for the area to increase? So we got a positive answer. The radius increases by 3 over 8 pi meters per second, which if you wanted to see that as a decimal, that might help you kind of figure out what's happening to make the area grow by 3 meters squared per second. The radius increases by the 3 over 8 pi meters per second.